In this work, we introduce capability-aware shared hypernetworks, or CASH, for learning flexible heterogeneous multi-robot coordination. Consider a scenario where fire departments gather their diverse firefighting robots to suppress a wildfire. These robots must assume roles in real time based on robot capabilities and environmental factors, adjusting to team changes and damages. Current approaches exist on two ends of a spectrum, one being parameter-shared approaches conditioned on a robot-specific identifier, and the other being individual policies learned for each robot. Parameter-shared approaches are efficient and can generalize to new robots, but tend to produce limited behavioral diversity. In contrast, individually learned policies tend to produce greater behavioral diversity but are inefficient and cannot generalize. We propose CASH, a general-purpose soft-weight sharing architecture that uses hypernetworks to enable a single set of parameters to dynamically adapt to each robot and the current context. We evaluate CASH in two sets of experiments, one conducted in JAXMARL, a state-of-the-art simulation platform, and the Robotarium, a state-of-the-art multi-robot hardware platform. We find that individually learned policies, labeled INDV, offer no advantages over CASH, as CASH can learn the appropriate level of behavioral diversity to achieve the same task performance more efficiently than individual learning. Next, we compare CASH to two baselines representing existing shared parameter approaches, where RNNP represents the paradigm of implicitly reasoning about heterogeneity through observations, and RNNEXP represents the paradigm of explicitly learning about heterogeneity by concatenating capabilities to observations. CASH learns performant policies across value-based learning, policy gradient learning, and imitation learning with fewer samples and 60 to 80% fewer parameters. Furthermore, CASH can better generalize to unseen robots and teams than baselines, as CASH has the highest success rate in all out-of-distribution evaluations. We note that CASH policies generally exhibit a higher behavioral diversity, which we hypothesize contributes to its superior generalization performance as CASH can better adapt its learned strategies through diverse behaviors. Evaluating CASH in the material transport and predator capture-prey tasks in the Robotarium, we find that CASH's benefits extend to multi-robot systems, achieving higher returns when run in both tasks on real robots. We visualize and analyze rollouts in the Robotarium multi-robot platform to better understand CASH's performance compared to baselines. In material transport, we observe that CASH learns to effectively control the robots of varying speeds, while other baselines appear to struggle as illustrated by robots oscillating or stalling. We observe that CASH more frequently reasons about trait-based allocation compared to other baselines. For example, if a slower robot is closer to the far loading zone, it might still yield to the faster robots. The faster robots, despite being further from the distant loading zone at the current time step, can complete a round trip to the drop-off zone more quickly than the slower robot. Similarly, in the predator capture-prey scenario, CASH reasons about capabilities to learn a role-based strategy where capture robots loosely follow sensing robots, and converge on a prey's location once informed by the sensing robot. In contrast, other baselines seemingly struggle to reason about role assignment, frequently resulting in prey being sensed but not captured. We introduced CASH, an uncompromising middle ground approach between shared and individualized parameter approaches that is deployable on decentralized teams and supports imitation, value-based, and policy-based RL.